Welcome back to this lecture series on textile finishing. So, before we go further, let us see what we had done till now. In the last lecture, we tried to understand what is the Baeyerstrain theory, that whenever there are cyclic compounds, a 3-membered, 4-membered ring, there is a strain on the bonds, and because of that those compounds or those systems become more reactive. And so, we have unstable, relatively less stable structure, and so it becomes more reactive because there is a strain, and everything in this world would like to release the strain. So, one of the ways of releasing strain is just break the bond whenever the conditions are suitable. That is what we learned. And the aziridine compounds were some of those compounds which were 3-membered rings and could react with, let us say, the hydroxyl group of cellulose. So, in the last lecture we did learn about various compounds which were non-urea based compounds, which can be used for cross-linking on cellulosic fabrics like cotton and viscose. So, one of them, as we just mentioned, was azididenyl compounds, which sometimes are also known as epimines. And others were the isocyanates, which can react, as we know, with alcohols, which is like cellulose, hydroxyl groups of cellulose, and also pyridinium salts, which reacted as if they were chloralkyl compounds. What was the byproduct at the end of the day was a pyridine and an acid like HCl. So, all of these were non-urea based nitrogenous compounds. All right. So, they had nitrogen, whether through the pyridine part of it or through the isocyanate part of it or the azididenyl group. So, today we will discuss some of the non-nitrogenous agents which can be used for cross-linking. Interestingly, the formaldehyde which has been used to prepare N-methylol compounds, you remember, itself can be used for cross-linking. This compound in acidic solutions can react with cellulose hydroxyl groups, and also at lower temperatures. We may not like to go in for a pad dry cure process because formaldehyde may get evaporated. For various reasons you may not like it, but people have used it in wet cross linking. While the fabric is wet, the formaldehyde is in a solution, and the cross linking can be affected in acid medium, and you may get a cross link of this type right. Which type of link is this? This is also ether. Of course, some byproducts can also be formed where only reaction of this type may take place. So, it is not a cross link, but the formaldehyde has been attached. This type of reaction is also possible. There can be other type of reaction possible also, but definitely this does not have nitrogen, right, does not have nitrogen. no nitrogen. But we, for various reasons, may not like to use today a formaldehyde directly onto the textile, because as we know there can be some issues with the formaldehyde used directly on textiles. So, why should we not use, let us say, the formaldehyde, or why formaldehyde always will be remain a part of discussion in various forums? Fishy odor we already know. So, one is the smell itself, which people may obviously not like, and that is why we shifted slowly from dimethylol urea to dimethylol ethylene urea to dimethylon dihydroxyethylene urea, and their various products, substitutes, derivatives, because we wanted to reduce this compound, didn't want it to go into the water, didn't want it to smell while the fabrics are stored. But today people are also talking about that this formaldehyde could be a health hazard. If that becomes true, then obviously one will like to avoid it, and therefore we said we will talk about some compounds which are non-formaldehyde based compounds. There have been some studies on animals like rats, where it has been shown that formaldehyde can cause some cancer, although till today this has not been detected on any human, but still people have started looking the release of formaldehyde as a serious problem, and not because of odor, but because of the health reasons. And if that be so, then we may be tempted to discuss agents which would not release formaldehyde. So, as far as guidelines are concerned, people have said that the solutions of formaldehyde in water, if the concentration is more than 1, have a possible risk of damage, and damage obviously irreversible damage. So, if that happens, so people should avoid that, but 1% is a very large concentration. 1% would not be released from fabrics, right. But at lower concentration, much lower concentration, let us say concentration some in the range of 0.2% and a little above, may cause sensitization when you contact, when the skin comes in contact with such type of concentration, which is low concentration. But then, so these are some of the issues as far as the humans are concerned. So, people may therefore like to be more cautious for using any such compound. So, various standards have been set up across the world. One of them is an Oeko standard, which prescribes many types of compound which should be less than a certain percentage. As far as the formaldehyde is concerned, the limits have been defined. This is one of the examples. So, it is a universal kind of an acceptance. For products which are for babies, you would like it to be less than 16. In fact, you would like it to be 0, but then 0 can be there only if you do not use it. So, less than 16 milligram per kilogram is what type of standards that people may like to agree. If it is next to skin, like underwears and so on and so forth, garments which touch the skin, it should be less than 75. If there is no direct contact with skin, then maybe 150 such type of products could be there which have require less than 150, and if they are decorative material like curtains and other such stuff, then you may have a standard which is less than 300 milligram per kilogram. So, as far as the standard is concerned, they are also not obviously looking at a zero release of formaldehyde, but obviously limited release, very low release may be okay, but more than this will be questioned. So, that is why it is good to talk about compounds which can cross-link and are formaldehyde free, or they do not use formaldehyde in their preparation. So, what is the best way forward? The best way forward is do not use it. Right? So, we did learn about other chemicals which were epimines, isocyanates, pyridine salt. They also do not have formaldehyde in them. So, well, okay, nitrogenous, do not have formaldehyde, you can use them. Of course, they may have other difficulties, for example, pyridine itself which comes out as a byproduct may not be the best thing to happen. Isocyanates are also very reactive and their storage is an issue, obviously will be an issue, and they cannot be applied through aqueous medium, various kinds of things can happen. So, although these do not have any issues as far as the formaldehyde release is concerned, but it is good to have some options other than these compounds as well. So, today we will talk about non-nitrogenous compounds which are also, let us say, formaldehyde free. Okay. So, one of the compounds which is very potentially an important compound for cross-linking are epoxy based compounds. All right. So, CH2 and so they are in some way a 3-membered ether compounds. Okay. 3-membered ether compounds. Now, these are very important compounds and used for many purposes, but can be used for cross-linking also. Because they are 3-membered means what? It means they are also reactive. That means they can also react at lower temperatures and give you a covalent bond. They would require alkaline medium to be active, and they, as we said, can work at lower temperatures. Sometimes you may also use them from solutions, and pad dry cure may or may not be the option. Therefore, people have used it for wet cross-linking also. Let me again remind, wet cross-linking means that the fabric is wet. Another interesting option of this type of thing, one is a pad dry cure where the fabric is padded, dried and then cured. Other is wet cross-linking when the fabric is actually in the solution. Today people are talking about a middle path which is called the moist cross-linking. At the moment we are not discussing about that, but we are looking at the epoxy compounds which can be used for cross-linking. And obviously, you can see that these compounds have no formaldehyde. So, very simply, I mean, organic chemists get excited whenever they want to create a new molecule. So, very easy to create molecules based on what we call as compound which are diepoxides. This R1 which is holding these two groups on both sides can be anything, very aliphatic, aromatic, long chain, short chain, depends on what you want to do, and we can appreciate that if the length of the chain will change, molecular chain, then the properties are expected are going to be different, but nevertheless it gives a good opportunity for us to look at the epoxides. So, how does it react, let us say with cellulose? So, we said they will react in with cellulose and form a link So, if you have two molecules of cellulose, then one can form this cross link of this type. Now, what is this? It has again formed two ether groups. So, the only thing that has changed is the link in between. This, as I said, this if it is R1, then this also can be R1. So, you can have, but at the interestingly the two hydroxyl groups which have been used for making a cross link are generated because of this ethoxy ring. So, in some way the hydrophilicity of the cellulose is going to be maintained, right. And remember, is this reaction is an addition reaction. Okay. There is ring opens and cellulose or any other hydroxyl group for that matter, alcohols can also react, and you will get additional group, pendant group, which is the hydroxyl group. So, two hydroxyl groups have been cross linked, two have been created. Interesting compound in this category is epichlorohydrin. So, it is an epoxy compound which has a chlorine available also, but once the reaction takes place this chlorine can go. So, if somebody wants to say, well, I like to use epichlorohydrin as a cross linking agent, then one would always get confused as to how an epichlorohydrin can give a cross link. It can only give a covalent bond with one hydroxyl group being engaged, but it appears that this compound can actually form cross links. So, this cross linking obviously like in the other case also happens by ring opening mechanism. Let us say we have cellulose and then we have our epichlorohydrin. In alkaline conditions, the ring opens and you will get one link of the type that we just saw. So, one link is formed, and now after formation of the link, we do not have any epoxy group left, and then people then say, well, this is not a cross link. So, what happens is that this particular compound in alkaline conditions again will lose this HCl, which will get neutralized, and then you can get this anyway was already reacted, and then we get you see that. So, one reaction after having it is the epoxy group has again been reformed. Now, if it has been reformed, then obviously it can ring, it can cross link, or it can react. For example, now we are talking about, so we had cellulose and an epoxy group attached to this cellulose. This is the what? And then again in the alkaline medium, you can get in the presence of cellulose another molecule, one can get right. So, you get cross link even with epichlorohydrin, that is epichlorohydrin by itself has got one single epoxy group, but an interchange takes place after one cross linking. So, you have ring breaking, then ring formation, and then opening, and then cross linking, all that can happen. So, an epichlorohydrin can also make a cross link, right. Then there are other compounds which are called disulfones. You may have been taught about reactive dyes which are called vinyl sulfone based reactive dyes. Sometimes they are also known as remazoles. All right. So, that type of a group reacts with cotton and also with silk and wool in alkaline medium. The covalent bond can be formed. Now, instead of that, we can have a simple compound like this, for example, divinyl sulfone. So, instead of having one group, you got two groups. All right. So, theoretically it can cross link. So, it will react in alkaline medium like the reactive dyes, and it can cross link with cellulose, and what will be formed? Interestingly, If you see this, also is an ether link being formed. So, you can have cross links. Of course, there is one sulfur has come in between, but that is okay. But it can react with with cellulose, and if these groups had reacted earlier with reactive dyes, so you can always have situation they will react. I mean the groups which were used in reactive dyes for reaction with cellulose and wool and silk. So, they can also react with cellulose, wool and silk, that is silk and wool are basically proteins, right. So, you have some other option. So, you have the epoxy option, you have a divinyl sulfone option. Then there are other compounds which are not formaldehyde, but glyoxal. This compound is used these days, is suggested to be used these days in acidic medium approximately compound. Some of the catalysts like aluminum sulfates could be used, and you can go through a pad dry cure process, you can go through a moist cure process, and one can get a cross link. So, one can think of mild conditions and reactions can happen. Okay. So, if this will cross link with the cellulose, so you are likely to get reactions of this type. Does it remind you something which we just discussed with the epoxy compounds also making 2 hydroxyl groups, right, 2 hydroxyl groups. So, you again have no problem of hydrophilicity as such. Only thing is in between these there is no group, all right. So, this area is just CC bond, carbon carbon bond, but interesting. People found it's a very good replacement for as a cross linking agent which can use conventional pad dry cure methods. In acid medium, obviously if temperatures can be less, you can obviously have less losses due to heat. From the performance point of view, now we are looking at performance, means that you keep washing many times and over, and then what happens? People found that one other alternative using this could also be as best and give better performance actually. So, in this case we had seen that the link obviously is what type? Ether. So, for reasons that we want to improve the performance, so people said if we have glycol along with glyoxal, then it is possible that we may be able to create a cyclic structure and performance could be better, that we are looking at hydrolytic stability, that we do not want the bond to break easily, so that the performance is better. So, if we use glycol, this is what we call as a glycol. You see a similar compound, but that was glyoxal and glycol, similar looking compound. This is basically hydroxyl based system. Where do we use glycol otherwise? You remember somewhere we use glycol? In textile? Yeah, in the manufacture of polyester itself, you need glycol, isn't it? Okay. So, this compound by itself may not be obviously the choice. What happens is when you use along with glyoxal, you can make a ring structure. So, the 2 hydroxyl groups, remember the 2 hydroxyl groups which are there, those two hydroxyl groups can then react, and by a dehydration process, and so you get a cyclic ring. By this the performance improves, and so this is one of the very good alternatives to N-methanol compounds which people have been suggesting, which is also formaldehyde free. The other compounds in this category are going to be in the class of polycarboxylic acids. Polycarboxylic acids obviously have more than one carboxylic acids. Carboxylic acids in mild alkaline conditions can react with alcohols to create a covalent bond. What is that bond? Bond will called to be ester bond. Okay. So, if there are theoretically if there are two carboxyl groups and you can create two ester links, so you can obviously make a cross link. So, that is why the polycarboxylic acids have become interesting for the finisher. Various types of polycarboxylic acids are available, like succinic acid is one which you probably recall. Simple carboxylic acid. Other carboxylic acid, citric acid, which has 3 carboxylic acids in its structure. But if you recall, it is also a hydroxy acid. So, this is also an example of polycarboxylic acids. Another interesting example is BTCA, which is butane tetracarboxylic acid. Butane tetracarboxylic acid, commercially these days people just say BTCA, and an interesting compound, and this compound would be something like this. So, there is a butane, all right. So, butane tetracarboxylic acid. So, there are some of the examples, one can always have more examples. Now, the question is, can all of them be considered as good cross-linking agents? The mechanism of reaction, now remember, we have to have conditions where the fabric does not get deteriorated and you are able to do the reaction, and therefore, the conditions that people are obviously using is approximately this 150 degrees mild alkaline conditions. One of the catalyst which is quite popular is mild alkaline is hypophosphite sodium salt of hypophosphite. Now, the mechanism of formation of a cross-link, let us say with cellulose, goes via an anhydride formation mechanism. If you can form an anhydride, then under these conditions reaction can take place. Under more severe condition, reaction can take place even without this, but let us say we are looking at conditions which are suitable for our textile finishing. So, let us say, so what happens is, so you have a polycarboxylic acid. Under the conditions, it first will form an anhydride. So, you first form anhydride Anhydride formation is like a dehydration reaction, right? And then in the presence of the conditions that we have mentioned, if you have cellulose also present, then we can expect reaction of this type. And this, after this reaction, will be back to carboxyl group. So, the anhydride breaks, reacts with cellulose and makes this link, and the other group of the carboxyl group is now free. Now, this carboxyl group, the second carboxyl group that we are referring here, can also react with cellulose only if there is a possibility of formation of an anhydride link again. Okay? If that does not happen, then under these conditions cross-linking will not be possible. So, let us go back. Look at this BTCA. Can it form anhydride and crosslink? Yes, of course. These two groups can form anhydride, these two groups can form anhydride, and they can form crosslinks, and after crosslinking you can have free carboxyl groups. So, there are various combinations that are possible in the BTCA. The most popular may be this one, where the two end carboxyl groups do anhydride the formation and then the reaction takes place and then you get the crosslink. We go back again and let us see citric acid. What will the citric acid do? The citric acid also will be able to make first anhydride group, make a covalent bond, then one of them will be released, then the two of them will make another anhydride. So, first anhydride, then the second anhydride formation, and you will again get a crosslink. Okay. If we go back further, then this is succinic acid. Can we make? Yes, of course. First anhydride will be formed, a link will be made, and after crosslink, after covalent bond has been made, you will get one free carboxyl group, but then this free carboxyl group has no other near carboxyl group with which it can make an anhydride. So, if it can't make anhydride, it will not be able to cross link. So, among the polycarboxylic acids also, succinic acid for that matter will not be able to make cross link. It can only make one link, which is a covalent link. All right. So, this is where we are, and so we are now asking another question. What type of a link? Ester. Right, will form an ester link. In many cases before that you saw, what links were more or less, most of the links were ether links. All right. So, the difference between the stability of these two rings is the ether links are more stable in alkaline conditions. Let us say you have washing conditions which are alkaline, and if the washing conditions are acidic, then the ether links may have some difficulty in stability. Reverse is the case here. Ester links are less stable or more susceptible to alkaline hydrolysis. So, these are the differences between the ester and the ether links. So, that is one. Let us see if there is anything other possible. One of the interesting possibilities is using an acid chloride. Acid chloride. Now, do you remember this? If this was, let us say, instead of Cl, if this compound was this, what do you think is this compound? Terphthalic acid. You remember earlier we talked about ethylene glycol, now we are talking about terphthalic acid, you can make polyester out of it. But the reactivity of this is much less compared to an chloride, very highly reactive compound. These type of compounds can be used to do the reactions at room temperature. But at the end of the day, what will they form? What will they form? They will also form, let us say, with cellulose, groups of this type. And if you have second cellulose molecule, then we would get another link which will be with another cellulose hydroxyl group. So, if we look at this compound and any polycarboxylic acid compound, the difference is here the reaction can take place without formation of anhydride. But remember, this is chloride of an acid and not the acid itself. So, they are reactive. So, at room temperature or little low temperatures, these reactions are possible. So, what have we learnt here? We have learnt that today there is preference for formaldehyde free finishes. And some of the examples that we can talk about is Glyoxal, glycol combination. Other that we can talk about is polycarboxylic acids. Polycarboxylic acids, and of course acid chlorides. Okay. So, if we use these compounds either at a temperatures which are mild temperatures of 120 degrees centigrades or temperature around 150 160 degrees centigrades, or at room temperature, some of these agents can give you crosslinks without involvement of any formaldehyde. So, some good compounds. So, we stop here, and next time when we meet we will discuss some other topic on finishing. Thank you.